Hello, my name is Sergey Taktai, and today I'm going to explain how to synthesize 4R5S, 4-ethyl, 5-fluoro, 5-methyl to heptanone from 4R, 5S, 4-ethyl, 5-fluoro, 5-methyl heptatwoine. And that is a mouthful. That is the IUPAC names of two molecules, one of which is our product and the other is our reagent. And in order to be able to do any of that, we first need to break that down and turn it into a skeletal structure and a molecule we can see and understand. So, according to IUPAC, we have here the parent name of the longest carbon chain, hept, and that is 7. Then known is a suffix for the ketone, and these are all substituents in alphabetical order, and the numbers that are in front of them are the corresponding carbons. So let's go ahead and draw a 7-carbon chain. 1, 2, 3, 4, 5, 6, 7, and number it. 1, 2, 3, 4, 5, 6, and 7. And we have on the fourth, we have an ethyl, and since we can see that there's a RS notation, that is a stereochemistry that indicates 3-dimensional orientation in space. So we are going to plug the substituents in using the dash wedge system. Dashes are in the back of the plane, wedges are out of the plane, and I'll explain it as I go on. So let's go. 4, we have ethyl. Let's just say 4 is going to be a dashed ethyl group. Dash means the carbon chain is in the plane of the board. The dash indicates that this ethyl group is going into the plane of the board. So it's going into the board, whereas a wedge, means a wedged, implied wedged hydrogen here means it's coming out of the board. So we've got 4-ethyl, then we have 5-fluoro, and let's just say fluoro is going to be a wedged fluoro here, fluorine, and we have a methyl group, and we're going to have to dash that. Okay, and because it is a one or a ketone on the second carbon, all that is, there's a carbonyl group, right? Double bond carbon to oxygen here. And now let's address the stereochemistry of it. So the rules for that are, we need to prioritize each one of the groups around the stereocenter. The stereocenter is an atom that has 4 different groups, which means it has to be sp3 hybridized. So we've got, and the priority is set by the atomic number. So the higher the atomic number, the higher the priority. So here we have carbon from here. This carbon is bonded to a carbon here, and a carbon there. Those are all tied 3 carbons. H is lower than carbon, so it's the lowest priority. We just put 4th here. Then how do we break the tie? Is we move out to the next bonded atom. So here, this carbon is bonded to another carbon. This carbon is bonded to another carbon, and this carbon is bonded to a fluorine, which is a higher atomic number, so we give this first priority. Then you can clearly see that this ethyl, to break the tie between the 2 carbons, we have to go out again, and there's nothing else to go out to, but here is an oxygen, so this is the second priority, and this is the third. This hydrogen is the 4th. And so we kind of draw a circle going into increasing number of priorities. Boom. So it's going to the left. Left is S. S for sinister. S. Okay. And here we have an R. But what we need to know is another rule, is that the lowest priority atom has to be, or the lowest priority group has to be in the back. So it has to be a dashed system. Otherwise, if it's not in the back, then you have to flip it, and our lowest priority is not in the back, so we have to flip that into an R. So that is correct. If the H would have been in the back, then it would be incorrect, because it'd still be this way, but we wouldn't have to flip it. So we flipped it, it's R, that is correct. Let's see the 5 carbon. F is clearly the highest priority, so 1. Then we have carbon here, carbon here, carbon here, breaking the tie, we're going out. Carbon, carbon, nothing here, so it's one of these, that's first priority, and it's clearly this one, because it goes further and there's an oxygen here. So this is going to be the first priority, this is going to be the second priority, and this is going to be the third priority, and it's going to go in, I'm sorry, I meant to say this is the second, so that's the first, this is the second, this is the third, and it's going to go in this direction here, boom. Our lowest priority is in the back, so we don't need to flip it. It is going to the left, so that is again S. Orientation, and because the lowest priority group is in the back, we do not need to flip it, so it is in the right orientation, and that is the right layout of the stereochemistry around that carbon, and that agrees with our 5s here. So that is our product here. This is what we want to achieve. Now let's look and try and draw out what we have for our reagent. And again, it has hept 7 carbon chain. Everything else is the same, so we can just keep that. But here it's 2-ine, which means alkyne, and the second carbon, there's an alkyne group there, which means there's a triple bonded carbon to another carbon. So let's draw out the 1, 2, 3, 4, 5, 6, 7. Well, leave them. Everything else is the same, so we might as well just throw in the fluorine here. No need to go through all of that mess. Then we've got the ethyl group here, then we have our hydrogen right there, and we have our ethyl group here. Now the only difference is, at the second carbon we have a triple bond with the third carbon, right? And that makes it hept2-ine instead of heptanone. Triple bond instead of a carbonyl group. So we know that these carbons here are sp hybridized, which means they have to be linear to be accurate. So we need to erase this bending here and draw out a straight line. Boom, triple bond, we got 1, 2, 3, 4. Now that is a correct layout of our, so we need to have a reaction that turns this into that. Because the reaction we need to do requires a lot of space, what I'm going to do to save space and time, I'm just going to take this whole thing here, boom, which is the same as this whole thing here, right? And I'm going to name it R prime. Alkyne is our reagent, ketone is our product. The reaction we need to undergo to achieve our product is the addition of water reaction. That reaction will occur if you add water and sulfuric acid to the solution, in a solution with our reagent. So once we add those together, what's going to happen first is an acid-base reaction to where the water is going to get protonated by the sulfuric acid. So the electrons from the water are going to attack that hydrogen proton and steal it away, leaving a weak base in the solution. But that's not important because it doesn't do any important function here. So we're going to create a hydronium ion, which is an oxygen bond with 3 hydrogens with a positive charge. And one of our pi bonds from our alkyne is going to attack the proton on this hydronium ion and steal it, and the remaining electrons are going to go onto the oxygen. So what we're going to get from that is we're going to have our okay, there we go. Like that. We're going to have a carbocation here, positively charged. This is now sp2 hybridized. And then here we're going to have our hydrogen bonded to our R' group. And we're also going to have our H2O present. And this H2O is now an nucleophile, and this electrophile is going to want to be attacked by this nucleophile, so the electrons are going to go boom from the oxygen and attack that electrophile carbocation. So what we're going to get from that is this. It's going to be oxygen bonded, positively charged, to double bond our methyl group. We have our hydrogen here and our R' here, like so. And there's also always more water in our solution. So one of those water molecules that are just hanging around there are going to H2O attack this acidic hydrogen now, and the electrons are going to go right back to this oxygen, giving us another hydronium and an alcohol bonded now to the double bond methyl here. Then we have our hydrogen there and our R group, like so. And then our hydronium is, let's just say it's over here. Each hydronium ion. Boom. Like so. So this other pi bond is going to want to go and attack the proton here and steal it. So what we're going to get from that is, now we have hydrogen, oxygen bonded to carbocation, positively charged, third order, and here we're going to now have two hydrogens and our R group. Okay, so then this is actually, let's make sure we see here, actually, this is a resonance stabilized carbocation, and its resonance structure is, we could have these electrons go onto the bond here to stabilize that positive charge. And what we're going to get is an oxygen is now going to be a pair of electrons, positive, double bonded to that. And we're going to have two hydrogens here and our R group right there. So we also have our water here, H2O. And what's going to happen is these electrons on the oxygen are going to attack that acidic hydrogen so that the oxygen can lose that positive charge, and what we're going to get from that is our product, which is the ketone that we wanted. Ketone bonded here to two hydrogens and our R group. Well, yeah, these electrons are going to go on here.